Imagine for a moment that you're standing at a train station. A high-speed train rushes past you at 200 miles per hour. Now imagine you're on that train and you turn on a flashlight. Common sense tells you that the light from your flashlight should be traveling at the speed of light plus the 200 miles per hour of the train, right? Wrong. Dead wrong. And this isn't just a quirk of physics. This is the fundamental rule that makes faster than light travel not just difficult, not just improbable, but literally, physically, mathematically impossible. Here's the shocking part. Every single spacecraft we've ever built, every rocket, every probe, every ambitious plan to reach the stars, they're all prisoners of a cosmic speed limit that cannot be broken. Not because we lack the technology, not because we haven't been clever enough, but because the universe itself, space, time, energy, matter conspires against us in ways that will blow your mind. What if I told you that as you try to go faster, you actually get heavier? What if I told you that time itself slows down for you? What if I told you that reaching the speed of light would require infinite energy from an entire universe that doesn't even have infinite energy to give? And here's the real kicker. Even if you somehow had all that energy, you still couldn't do it because the math literally breaks down. You'd need to divide by 0. Reality itself says no. Over the next 4 hours, I'm going to take you on a journey that will completely transform how you understand speed, time, energy, and reality itself. By the end, you'll understand why the speed of light isn't just a speed limit. It's a fundamental property of the universe that keeps causality itself from collapsing. But before we dive into this mind-bending journey, do me a favor, smash that like button if you're ready to have your understanding of reality completely transformed. And hit subscribe because we're going deep into the most fascinating corners of physics on this channel. Also, drop a comment right now telling me where you're watching from and what time it is for you. I'm curious to see how many different time zones we're spanning as we explore why time itself behaves so strangely at high speeds. Seriously, comment right now. I read every single one. All right, let's start with what seems simple. Speed. You think you know what speed is, right? It's how fast something moves. If you drive 60 miles per hour, you're covering 60 miles in 1 hour. Simple math. Elementary school stuff. But here's where things get weird immediately. Speed is always measured relative to something else. When you're driving 60 miles per hour, you're going 60 miles per hour relative to the road. But the road is on Earth, which is spinning. So you're also moving at about 1,000 miles per hour relative to Earth's center, just from the planet's rotation. Oh, and Earth is orbiting the Sun at about 67,000 miles per hour. And our entire solar system is orbiting the galactic center at roughly 514,000 miles per hour. And our galaxy is moving through space at around 1.3 million miles per hour. So what's your real speed? The answer is, there is no real speed. Speed only exists in relation to something else. This is called Galilean relativity, and Galileo Galilei figured this out way back in 1632. He realized that the laws of physics work the same, whether you're standing still or moving at constant velocity. If you're on a smoothly moving ship, you can't tell you're moving without looking outside. Drop a ball, and it falls straight down from your perspective, even though to someone on shore, that ball is following a curved path. Think of it like this. Imagine you're on a perfectly smooth airplane, no turbulence, flying at 500 miles per hour. You toss a peanut to your friend across the aisle. That peanut doesn't suddenly slam backward at 500 miles per hour. It just arcs gently to your friend. From your perspective inside the plane, physics works exactly as it does on the ground. You're in what's called an inertial reference frame. Now, for centuries, this was fine. Speeds added up nicely. If you're on a train going 60 miles per hour and you walk forward at 3 miles per hour, you're going 63 miles per hour relative to the ground. If you throw a baseball forward at 90 miles per hour from that train, the baseball is going 150 miles per hour relative to the ground. Math checks out. Everyone's happy. But then came light, and light broke everything. In the 1860s, a Scottish physicist named James Clerk Maxwell was playing with equations about electricity and magnetism. He wasn't even trying to revolutionize physics. He was just trying to understand how electric and magnetic fields worked. But when he put his equations together, something bizarre popped out. A wave that moved through space at a specific speed. When he calculated that speed, it came out to about 186,282 miles per second. Maxwell looked at that number and realized that's the speed of light. Light wasn't just some mysterious thing. It was an electromagnetic wave predicted by the fundamental equations of electromagnetism. But here's the weird part. The speed came out of the equations themselves. It wasn't relative to anything. It was just a number, a constant. 299,792,458 meters per second, to be precise. We now call it C, and it's the most important letter in physics. This created a massive problem. If light is a wave, what's it waving through? Ocean waves move through water. Sound waves move through air. So light waves must move through something, right? Scientists called this mysterious substance the luminiferous ether, an invisible medium that filled all of space, through which light waves propagated. And here's where the story gets really interesting. If ether existed, then the speed of light should depend on how you're moving through the ether. Just like sound travels at 767 miles per hour through air. But if you're moving toward the source of sound at 100 miles per hour, you'd measure sound approaching you at 867 miles per hour. The same should be true for light and ether. In 1887, two American physicists, Albert Michelson and Edward Morley, set up what should have been a simple experiment. Earth is moving through space, right? So at different times of year, we should be moving through the ether at different speeds, sometimes with our orbital motion, sometimes against it. They built an incredibly sensitive device called an interferometer that could detect tiny changes in the speed of light based on Earth's motion through the ether. The result? Nothing. Absolutely nothing. No matter which direction they measured, no matter what time of year, no matter how they set up the experiment, light always traveled at exactly the same speed. Not approximately the same. Exactly. The same speed. This was like throwing a baseball from a moving car and having it arrive at the same speed, whether the car was moving forward or backward. It made no sense. The scientific community was baffled. Some thought the experiment was flawed. Others proposed increasingly bizarre explanations. Maybe Earth dragged the ether along with it? Maybe objects contracted as they moved through ether, perfectly compensating for the expected changes? The truth was far stranger than anyone imagined, and it would take a patent clerk in Switzerland to figure it out. Enter Albert Einstein, 1905. He was 26 years old, working in a patent office and thinking about physics problems in his spare time. He looked at the Michelson-Morley result and everyone's confused attempts to explain it, and he did something radical. He took the results seriously. What if light really does travel at the same speed for everyone, regardless of how they're moving? This doesn't sound that revolutionary, right? But watch what happens when you actually accept this as true. Let's go back to our train example. You're on a train moving at half the speed of light. Let's call it 0.5 c. Someone on the train turns on a flashlight, shining it forward. From the perspective of someone on the train, the light shoots forward at speed c, obviously. But what about someone standing on the ground watching the train pass? According to old school physics, they should see the light moving at 5 c, the train's speed 0.5 c, plus the light speed c. But Michelson and Morley showed this doesn't happen. The person on the ground also measures the light moving at exactly c, not 1.5 c, just c. Now your brain should be hurting because this seems impossible. How can two people moving relative to each other both measure the same light beam traveling at the same speed? The only way this can work is if something else is adjusting to compensate. That something is time itself. Einstein realized that time must flow at different rates for people moving at different speeds. This isn't a trick or an illusion. Time literally passes more slowly when you're moving fast. It's called time dilation, and it's one of the most experimentally verified facts in all of physics. Think of it like this. Imagine time and space are like a rubber sheet. When you move through space faster, the sheet stretches differently for you than for someone who's standing still. Your now becomes tilted relative to their now. Events that are simultaneous for you are not simultaneous for them. Here's a thought experiment Einstein himself used. Imagine you're in a rocket ship moving at 90% the speed of light. You have a clock on board, a light clock, where light bounces between two mirrors, and each bounce counts as one tick. From your perspective, the light just bounces straight up and down. Tick-tock, tick-tock. 1 second per second? But someone watching your rocket ship pass sees something different. From their perspective, while the light is bouncing up and down, your rocket is also moving forward. So the light's path isn't straight up and down, it's diagonal. The light has to travel farther to complete each tick. But light always travels at speed c for everyone. So if the light is traveling farther at the same speed, it must take longer to complete each bounce. Your clock is running slow from their perspective. Not broken, not malfunctioning. Actually, physically, genuinely running slow. And not just your light clock, every biological process, every vibration of every atom in your body. Time itself is passing more slowly for you. The equation is actually pretty simple. If v is your velocity and c is the speed of light, time slows down by a factor of 1, divided by the square root of 1 minus v squared per c squared. At everyday speeds, v squared per c squared is essentially 0, so the square root of 1 minus 0 is just 1, and you divide by 1, which means no time dilation. But as you approach the speed of light, v gets closer to c, so v squared per c squared gets closer to 1, which means you're dividing by the square root of something closer to 0, which means time slows down more and more dramatically. At 90% the speed of light, time slows down by a factor about 2.3. For every hour that passes on Earth, only about 26 minutes pass for you. At 99% the speed of light, the factor is about 7. At 99.9% the speed of light, it's about 22. 1 year for you is 22 years on Earth. And here's the kicker. At exactly the speed of light, you'd be dividing by 0. Time would stop completely. Not slow down, stop. You'd experience 0 time. From your perspective, if you could travel at the speed of light, you'd arrive at your destination instantaneously, no matter how far away it was. The entire journey would take 0 time for you. This is our first huge hint about why reaching the speed of light is impossible. The math literally breaks at c. Reality divides by 0. The universe says error, does not compute, but weight light itself travels at the speed of light, right? So why doesn't light experience this problem? The answer is beautifully strange. From a photon's perspective, it doesn't experience any time at all. A photon emitted from the sun reaches your eye instantaneously from the photon's perspective. It doesn't experience the 8-minute journey. Time doesn't exist for photons. They live eternally in a single moment. This is why only things with 0 mass can travel at the speed of light, because anything with mass would require experiencing 0 time, which would require dividing by 0, which breaks reality. We've been proving Einstein right for over a century now. In 1971, physicists Joseph Haffel and Richard Keating put atomic clocks on commercial airplanes and flew them around the world, once eastward and once westward. When they compared these clocks to atomic clocks that stayed on the ground, the flying clocks had actually ticked fewer times. They'd experienced less time. The difference was tiny, just a few hundred nanoseconds, but it was exactly what Einstein's equations predicted. GPS satellites have to account for time dilation, or they wouldn't work. These satellites are moving at about 8,700 miles per hour relative to Earth's surface, and they're experiencing slightly less gravity than we are on the surface. Both of these factors affect time. Motion slows time down, and weaker gravity speeds time up. The net effect is that clocks on GPS satellites gain about 38 microseconds per day compared to clocks on Earth. That might not sound like much, but light travels about 1 foot in a nanosecond. Without correcting for time dilation, GPS would accumulate errors of about 6 miles per day. Your GPS navigation would be useless within hours. Every single time you use GPS, you're proving Einstein right. Every single time you use your phone to navigate, you're relying on corrections for relativistic time dilation. The universe really works this way. So here's where we are. We've learned that time itself is flexible, that it slows down as you move faster, and that at the speed of light, time stops completely. This is the first major barrier to reaching the speed of light. The math breaks down. But this is just the beginning. Things are about to get even weirder. Okay, so time slows down when you move fast. Weird, but we can wrap our heads around it. But Einstein wasn't done messing with our intuitions. If time changes with motion, what about space? Remember, speed is distance divided by time. If time is changing, but the speed of light remains constant for everyone, then distance must also be changing. And it is. This is called length contraction, and it's just as real as time dilation. When you move fast, the entire universe in your direction of motion contracts. It actually gets shorter from your perspective. Let's say you're traveling at 99.9% the speed of light toward Alpha Centauri, which is about 4.37 light years away. From Earth's perspective, this journey should take you about 4.38 years, right? Just slightly longer than the distance, because you're going slightly slower than light. But here's the twist. From your perspective on the spaceship, time has slowed down by a factor of about 22, so the journey only takes you about 0.2 years less than 3 months. But wait, if you're traveling at 99.9% the speed of light, and the journey takes 0.2 years, then the distance you traveled must be 0.2 light years from your perspective, not 4.37 light years. The distance actually contracted. The space between Earth and Alpha Centauri got squished. From your high-speed perspective, Alpha Centauri is only 0.2 light years away, not 4.37. The universe itself is shorter for you. Think of it like this. Imagine the universe is a giant accordion. When you're at rest, the accordion is stretched out. As you start moving faster, the accordion compresses in your direction of motion. At 90% the speed of light, everything in front of you is squished to about 44% of its rest length. At 99.9% the speed of light, it's squished to about 4.5% of its rest length. At the speed of light, the entire universe in your direction of motion would contract to 0 length. Again, this isn't an optical illusion. This isn't what things look like. This is what they actually are, from your frame of reference. Space itself compresses. Now here's where your mind should really start bending. Time dilation and length contraction are two sides of the same coin. They're not separate phenomena. They're different perspectives on the same underlying reality. And that reality is that we don't live in separate space and time. We live in space-time. This was the insight of Einstein's former professor, Hermann Minkowski, who in 1908 declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." What Minkowski realized is that we should stop thinking of the universe as 3 dimensions of space plus 1 dimension of time. Instead, we should think of it as 4 dimensions of space-time, a unified 4-dimensional fabric where space and time are intertwined. Imagine you're looking at a pencil straight on. You see its length, let's say 6 inches. Now rotate the pencil so you're looking at it from an angle. From this new perspective, it looks shorter, maybe 4 inches from your point of view, even though the pencil itself hasn't changed. The length you see depends on your angle of view. Some of what was length from the first angle now appears as width from the second angle. Space-time works similarly. When you change your velocity, you're essentially rotating your perspective through 4-dimensional space-time. Some of what was space from one perspective becomes time from another perspective, and vice versa. What you measure as simultaneous events depends on your motion through space-time. This is why different observers moving at different speeds disagree about measurements of time and space. They're looking at space-time from different angles. But there's something that all observers agree on, no matter how they're moving: the space-time interval. It's like the actual length of the pencil, regardless of your viewing angle. The space-time interval combines space and time in a way that's the same for everyone. The equation is space-time interval squared equals time interval squared, space interval squared. The minus sign is crucial. It shows that space and time trade off against each other. Move more through space, experience less time. Move less through space, experience more time. And here's the beautiful part. Light always moves along what's called a null path through space-time, a path where the space-time interval equals 0. For light, the time interval exactly equals the space interval. This is why light always travels at the same speed for everyone. It's not really a speed in the conventional sense. It's the conversion factor between space and time, the exchange rate between the different dimensions of space-time. The speed of light is actually the speed of causality itself. It's the maximum rate at which cause can influence effect, the speed at which information can propagate through space-time. It's not really about light at all. Light just happens to travel at this fundamental cosmic speed limit because photons have no mass. Now, here's why this matters for our question about reaching the speed of light. As you approach the speed of light, you're approaching a kind of boundary in space-time. You're approaching the edge of possible paths through the 4-dimensional fabric of reality. Objects with mass can never reach this boundary. They can get arbitrarily close, but they can never cross it. It's not like a speed bump or a wall. It's more fundamental than that. It's like asking what's north of the North Pole. The question doesn't make sense. For objects with mass, paths through space-time that reach the speed of light simply don't exist. They're not forbidden by some cosmic traffic law. They're geometrically impossible in 4-dimensional space-time. Every single particle accelerator on Earth proves this every day. At CERN, the Large Hadron Collider accelerates protons to 99.9999991% the speed of light. That's insanely fast. Each proton is moving so fast that from its perspective, the entire 17-mile circumference of the LHC ring contracts to about 30 feet. Time slows down so much that unstable particles that would normally decay in microseconds can survive for what seems like hours from the lab's perspective. But here's the thing. No matter how much energy they pump into those protons, they can't reach 100% of the speed of light. They keep getting closer. 99.9999991%. 99.9999991%. Adding more and more nines, but they never actually reach C. The universe won't let them. Which brings us to the next barrier, energy. And oh boy, this is where things get really impossible. Let's talk about pushing things. In everyday life, if you want something to go twice as fast, you need to push it with twice as much force for the same amount of time, or push it with the same force for twice as long. Want to go 3 times as fast? 3 times the push. The relationship is linear. Simple, but relativity ruins this pleasant simplicity. As you approach the speed of light, pushing things becomes increasingly difficult. Not because of air resistance or friction. We're talking about objects in empty space. The universe itself resists your acceleration. Here's why. Einstein's most famous equation, E equals mc, tells us that energy and mass are equivalent. They're the same thing in different forms. But that's the simplified version for objects at rest. The full equation, which includes motion, is E equals mc, where gamma is that same time dilation factor we talked about, 1 divided by the square root of 1 minus v squared per c squared. At everyday speeds, gamma is basically 1, so E equals mc. No big deal. But as you approach the speed of light, gamma starts growing. At 50% of light speed, gamma is about 1.15. At 90%, it's about 2.3. At 99%, it's about 7. At 99.9%, it's about 22. What this means is that as you go faster, your energy increases much more rapidly than your velocity. You're not just adding kinetic energy, you're increasing your relativistic mass. From an external observer's perspective, you're getting heavier and heavier the faster you go. Think of it like running through water. When you first start moving through water, it's not too hard. But as you try to go faster and faster, the water's resistance increases dramatically. You can keep speeding up, but it requires exponentially more effort for each increment of speed. Approaching the speed of light is like that, except instead of water resistance, it's the structure of space-time itself that resists. Let's put some numbers to this. Say you have a spacecraft with a mass of 1,000 kilograms. At rest, its energy equivalent is about 910 joules. That's 90 million trillion joules. The energy in about 21 megatons of TNT. Already enormous, just from the mass energy equivalence. Now accelerate it to 50% the speed of light. Its total energy is now about 1.15 times its rest mass energy. You've added about 15% more energy. Accelerate to 90% of light speed. Its total energy is now 2.3 times its rest mass energy. You've added 130% more energy more than its entire rest mass energy. Get to 99% of light speed. Its total energy is 7 times its rest mass energy. You've added 600% more energy. Push to 99.9%. Total energy is 22 times rest mass energy. You've added 2,100% more energy. See the pattern? Each increment of speed closer to C requires adding more energy than all the previous increments combined. The energy requirement grows exponentially, approaching infinity as you approach the speed of light. At exactly the speed of light, gamma becomes infinite. Your energy would be infinite. Your relativistic mass would be infinite. You would need infinite energy to reach the speed of light. Now let's be clear about what infinite energy means. It's not like a really, really large amount of energy that we don't have yet, but maybe could gather someday. It's infinite, limitless, more than exists in the entire observable universe, more than could exist in any finite universe. The observable universe contains maybe 10 atoms. If you converted every single atom in the entire observable universe into pure energy E equals mc, complete matter-to-energy conversion, 100% efficient, you still couldn't accelerate a single electron to exactly the speed of light. Because infinity is bigger than any finite number, no matter how large. Let me give you a sense of scale. The most powerful particle accelerator ever built, the Large Hadron Collider, uses about 1.3 terawatt-hours of electricity per year. That's 1.3 trillion watt-hours, enough to power about 130,000 American homes for a year. All that energy goes into accelerating 2 beams of protons, maybe a few nanograms of matter total, to 99.9999991% of the speed of light. To accelerate a single proton to 99.99999999999999999%, 15 nines of the speed of light would require more energy than the LHC uses in its entire operational lifetime. To get to 29s would require more than all the energy humanity has ever produced in all of history. To get to 39s would require more than all the energy the sun produces in a year. And we're not even close to the speed of light yet. We're still infinitely far away, because there's no amount of nines you can add that equals infinity. This is why when people propose ideas like nuclear pulse propulsion or antimatter engines as ways to reach near light speeds, physicists get skeptical. Sure, these technologies might let us reach 1% or even 10% of light speed, which would be absolutely revolutionary. But getting to 99% of light speed isn't 10 times harder than getting to 10%. It's hundreds of times harder. And getting to 99.9% isn't just a bit harder than 99%. It's exponentially harder. Let's think about what this means practically. The nearest star system, Alpha Centauri, is about 4.37 light years away. If we could somehow build a spacecraft that reached 90% of light speed, which would require energy, equivalent to millions of our most powerful nuclear bombs, the trip would still take about 4.9 years from Earth's perspective, and about 2.1 years from the crew's perspective, due to time dilation. To cut that time in half again, to reach 99% of light speed, would require more than triple the energy. And the improvement in travel time would only save you about a year from Earth's perspective, and less from the crew's perspective because of increased time dilation. The energy cost per unit improvement in travel time grows exponentially. There's a point where adding more energy gives you almost no practical benefit because you're fighting against an infinite barrier. It's like trying to fill a bottomless pit. No matter how much you pour in, you never get closer to filling it. But let's say you're stubborn. Let's say some future civilization has access to truly staggering amounts of energy. Maybe they've built a Dyson sphere that captures the entire output of their star, providing about 410 watts of power. Surely with that much energy, they could reach the speed of light, right? Wrong, because there's yet another problem. As you pump more energy into an object to accelerate it, that energy itself, as mass E equals mc, goes both ways. The energy you're adding to speed up the object is also making it heavier, which means it requires even more energy to accelerate, which makes it even heavier, which requires even more energy, and so on. You're trapped in an infinite feedback loop. The closer you get to the speed of light, the more energy you need, but adding that energy makes you need even more energy. It's not just hard. It's not just impractical. It's mathematically impossible. The equations lead to infinity, and infinity is not a place you can reach by adding finite amounts of energy, no matter how large those finite amounts are. This is our second major barrier, energy. But we're still not done. There are more barriers, each more fundamental than the last. Now let's talk about what's actually getting heavier as you accelerate. This is subtle and often misunderstood, so pay attention. You might have heard that mass increases as you approach the speed of light. This is sort of true, but also sort of misleading. Your rest mass, the mass you have when you're standing still, never changes. An electron at rest has a mass of 9.109 times 10 kilograms, and this never changes no matter how fast it moves. What does change is your relativistic mass, which is your rest mass, multiplied by that gamma factor. But modern physicists don't really like talking about relativistic mass because it's confusing. Instead, they talk about relativistic momentum and relativistic energy. In classical physics, momentum is just mass times velocity. P equals mv. Simple. If you double the velocity, you double the momentum. But in relativity, momentum is pgmv. That gamma factor appears again, and it changes everything. At low speeds, gamma is approximately 1, so P equals mv, and classical physics works fine. But as v approaches c, gamma approaches infinity, which means momentum approaches infinity, even though velocity is approaching a finite value. This creates a bizarre situation. As you add energy to accelerate an object, you're increasing its momentum, but you're not increasing its velocity as much as you'd expect. The momentum increases without bound, but the velocity asymptotically approaches c without ever reaching it. It's like running on a treadmill where the belt speeds up the faster you run. You're putting in more and more effort. Your energy expenditure is increasing, but your position relative to the room barely changes because the treadmill is compensating. The great physicist Richard Feynman, who won the Nobel Prize in 1965 for his work on quantum electrodynamics, described this beautifully. He said trying to accelerate an object to the speed of light is like pushing a boulder up an increasingly steep hill that becomes vertical as you approach the summit. No matter how hard you push, the hill just keeps getting steeper. The summit, the speed of light, is infinitely far up a vertical cliff. Let's think about what this means for a spaceship. Imagine you're on a spacecraft with a powerful engine that can provide constant thrust, let's say 1 g of acceleration, so you feel normal Earth gravity. From your perspective inside the ship, everything seems fine. You're accelerating steadily, and you feel like you're gaining speed at a constant rate. But from Earth's perspective, something strange is happening. At first, your velocity increases steadily, just as expected. But as you get faster, your rate of acceleration from Earth's perspective starts to slow down. You're still burning fuel at the same rate. Your engines are still producing the same thrust, but your actual velocity is increasing more and more slowly. By the time you reach 90% of the speed of light, you could run your engines for a year and barely increase your velocity at all from Earth's perspective. You're dumping enormous amounts of energy into acceleration, but nearly all of that energy is going into increasing your momentum without significantly increasing your velocity. The relationship between energy and velocity has become highly nonlinear. From your perspective on the ship, you still feel like you're accelerating normally. Time dilation and length contraction conspire to make everything seem consistent from your point of view. But from Earth's perspective, you've hit a wall that gets thicker and more impenetrable the harder you push against it. This is fundamentally different from any engineering challenge we've ever faced. Usually, if something is hard to do, we can overcome it with more resources, better technology, cleverer engineering. Can't lift something? Build a stronger crane. Can't go fast enough? Build a bigger engine. Can't generate enough power? Build more power plants. But this isn't an engineering problem. It's a mathematical impossibility baked into the structure of space-time. It's like saying, I want to draw a square circle, or I want to count to infinity. These aren't hard problems. They're nonsense problems. The words seem to make sense, but they describe something that cannot exist. Here's another way to think about it. In classical physics, kinetic energy grows as the square of velocity. K pay mv. Double the velocity, quadruple the energy. Triple the velocity, 9 times the energy. Steep, but manageable. In relativity, kinetic energy is Ke equals gamma to 1, make squared. At low velocities, this reduces to approximately pay mv, so classical physics works fine. But at high velocities, that gamma factor dominates. Remember, gamma equals 1 square root 1v squared per c squared. As v approaches c, the denominator approaches 0, so gamma approaches infinity. This means kinetic energy doesn't just grow as the square of velocity. It grows much, much faster. At 10% of light speed, your kinetic energy is about 0.5% of your rest mass energy. At 50%, it's about 15%. At 90%, it's 130%. At 99%, it's 600%. At 99.9%, it's 2,100%. At 99.99%, it's 7,000%. See how the jumps get bigger? Going from 0% to 50% requires adding 15% of your rest mass energy. But going from 99% to 99.9%, a much smaller change in velocity, requires adding 1,500% of your rest mass energy, 10 times as much. And it keeps getting worse. Going from 99.9% to 99.999% requires adding about 5,000% more of your rest mass energy. From 99.99% to 99.999% requires about 15,000% more. The energy requirements grow exponentially, approaching infinity as you approach light speed. At exactly the speed of light, your kinetic energy would be infinite. Your momentum would be infinite. Your relativistic mass would be infinite. These aren't just very large numbers. They're literally infinite, unbounded, limitless. And here's the kicker. The universe doesn't have infinite energy to give you. The observable universe contains a finite amount of mass energy. Even if you could somehow convert every particle in the observable universe into energy and channel all of it into accelerating a single electron, you'd still fall infinitely short of reaching the speed of light. Infinity isn't just a very big number. It's fundamentally different from any finite number, no matter how large. It's a category error to think we could reach it by accumulating enough finite resources. It's like trying to build a staircase to heaven. Not impossible, because heaven is too far away, but impossible because heaven isn't the kind of thing you can reach with a staircase. This momentum barrier is our third major obstacle, and it's arguably the most fundamental one yet. But believe it or not, we still have more reasons why reaching the speed of light is impossible, and they get even stranger. All right, we've covered time dilation, length contraction, and infinite energy requirements. Those are all weird, but they're at least comprehensible. Now we're going to venture into territory that's genuinely mind-bending. What happens to cause and effect if you could exceed the speed of light? The answer: causality itself breaks down. The very notion that effects follow causes collapses. You could receive a message before it was sent. You could arrive before you left. The universe would descend into logical paradox. Let me show you why this is unavoidable. It all comes down to something called the relativity of simultaneity, the fact that observers moving at different speeds disagree about which events happen at the same time. Here's a thought experiment. Imagine you and your friend are in space, at rest relative to each other, separated by some distance. You each set off a firecracker at exactly the same moment. From your mutual frame of reference, these events are simultaneous. Now imagine a third person flying past both of you at high speed. What does she see? Because of the way space-time works, she does not see the firecrackers going off simultaneously. If she's moving toward your friend, she sees your friend's firecracker go off first, then yours. If she's moving toward you, she'll see yours go off first, then your friend's. This isn't an optical illusion caused by light travel time. We can account for that. This is a fundamental feature of space-time. Events that are simultaneous in one reference frame are not simultaneous in other reference frames. Now is relative. But here's the crucial part. This only works for events that can't influence each other. Your firecracker and your friend's firecracker are separated by space, and they're set off simultaneously in your frame, which means no signal could travel from one to the other at or below the speed of light. These are called space-like separated events. For events that are connected by cause and effect, time-like separated events, all observers agree on the order. If event A causes event B, and a light signal could travel from A to B, then every observer, regardless of their motion, will agree that A happened before B. Causality is preserved. The speed of light is the boundary between these two regions. Light moves along what's called the light cone, the edge between space-like separated events and time-like separated events. Anything moving at or below the speed of light stays inside the light cone, where causality is preserved. But if something could move faster than light, it could cross outside the light cone. And that's where everything breaks. Here's why. Imagine you have a faster-than-light, FTL, communicator, some device that can send signals instantly across any distance. You send a message from Earth to Alpha Centauri, 4.37 light-years away. The message arrives instantly in your reference frame. Now, someone on a spaceship moving at high speed relative to Earth uses their FTL communicator to send a reply back to Earth. In their reference frame, they're sending the reply back instantly. But here's the problem. Due to the relativity of simultaneity, the instant they're sending the reply in their frame corresponds to a time in the past in your frame. The reply could arrive back on Earth before you sent the original message. You've just created a causal loop. Effect preceded cause. You received a reply before sending the message. The universe has tied itself into a logical knot. This isn't just a weird quirk. This is a fundamental violation of causality. And if causality breaks down, logic itself breaks down. You could have events that cause themselves, or events that prevent their own causes. The whole notion of physical law becomes meaningless. Stephen Hawking proposed what he called the chronology protection conjecture, a somewhat tongue-in-cheek suggestion that the laws of physics conspire to prevent time travel and causal paradoxes. While this isn't a proven theorem, it captures an important insight. The speed of light limit seems to be the universe's way of protecting causality. Think of it like this. The speed of light isn't really about speed at all. It's about the structure of cause and effect. It's about preserving the logical consistency of reality. Events can only influence other events that are within their light cone, their sphere of causal influence. The speed of light determines the maximum rate at which causality can propagate. If you could exceed the speed of light, you wouldn't just be moving really fast. You'd be breaking the logical structure of space-time. You'd be creating a reality where effects can precede causes, where the future can influence the past, where the very notion of before and after becomes meaningless. The physicist John Wheeler, who coined the term black hole and was Richard Feynman's PhD advisor, put it beautifully. Time is defined so that motion looks simple. The speed of light is the speed. It is precisely so that causality remains consistent, so that the universe obeys logical rules, so that physics is possible at all. Now, you might be thinking, okay, but what if I just accept the causal paradoxes? What if I'm okay with receiving messages before they're sent? But this isn't a matter of personal preference. The mathematics of relativity shows that if FTL travel were possible, you could construct scenarios that lead to logical contradiction situations where an event both does and doesn't happen. Imagine you build a machine that receives FTL messages from the future. You program it with a simple rule. If it receives a message, it does not send that message. If it doesn't receive a message, it sends one. This creates a paradox. If it sends a message, it receives the message and therefore doesn't send it. If it doesn't send a message, it doesn't receive one and therefore does send it. This isn't like the grandfather paradox in science fiction, which might have weird resolutions like alternate timelines. This is a logical impossibility in a single, consistent spacetime. The universe literally cannot be in a state where this machine both sends and doesn't send the message. It's a contradiction, like saying this statement is false. The only way to avoid this contradiction is to ensure that F2L communication is impossible. The speed of light isn't just a speed limit, it's the speed of causality, the speed at which information can propagate, the speed at which one event can influence another. And here's something that will really bake your noodle. From a photon's perspective, something traveling at the speed of light, it doesn't experience time at all. A photon emitted from a distant galaxy billions of light years away and absorbed by your eye experiences zero time between emission and absorption. From the photon's point of view, if we can call it that, It exists only at a single instant that encompasses both its creation and destruction. This is what it means to travel at the speed of light. You exist outside of time. Cause and effect collapse into a single eternal moment. Past, present, and future become meaningless. You're not moving through time anymore, you are time. Or rather, you're orthogonal to time, moving along a null path where time doesn't flow. This is why only massless particles can travel at light speed. They don't experience time, so they don't have a timeline, so they don't have causality in the usual sense. They're different from massive particles, not just in degree, but in fundamental kind. So here's our fourth barrier: causality. If you could reach or exceed the speed of light, you'd break the logical consistency of the universe. You'd make it possible for effects to precede causes, for futures to influence pasts, for paradoxes to become reality. The universe protects itself from this by making the speed of light an unbreachable barrier for anything with mass. But wait, there's more. We're about to dive into one of the most beautiful and bizarre aspects of relativity. The fact that the speed of light isn't just constant for everyone. It's the same in all directions, always and everywhere. And this seemingly simple fact has profound implications. Here's something that might seem obvious, but is actually deeply strange. Light travels at the same speed in all directions. If you shine a flashlight forward, the light goes at 299,792,458 meters per second. Shine it backward, same speed. Shine it left, right, up, down, always the same speed. You're probably thinking, well, yeah, obviously. Why would light care which direction it's going? But remember, you're moving. Earth is rotating, orbiting the sun, and the sun is orbiting the galactic center, and our galaxy is moving through the universe. We're moving in some direction through space at hundreds or thousands of kilometers per second. So if light is a wave in some medium, the old ether idea, we should be moving through that medium, and light should travel faster in some directions than others, relative to us, like how sound travels faster downwind than upwind. But it doesn't. Light travels at exactly the same speed in all directions, always regardless of how we're moving. This is called the isotropy of the speed of light, and it's one of the two fundamental postulates of special relativity. The other is that the laws of physics are the same in all inertial reference frames. These two simple postulates lead to all the weird consequences we've been discussing: time dilation, length contraction, mass energy equivalence, the whole package. But here's what's truly wild. The isotropy of light speed is actually impossible to test directly. Think about it. To measure the speed of light, you need to time how long it takes to travel a known distance. But to measure a distance and a time interval, you need measuring rods and clocks. And to synchronize your clocks at different locations, you need to send signals between them. But what speed do those signals travel? The speed of light. You're stuck in a circular argument. You need to know the speed of light to synchronize clocks, but you need synchronized clocks to measure the speed of light. It's like trying to measure a ruler with itself. What physicists actually do is assume that the speed of light is the same in all directions. That's the isotropy assumption. And then they use this assumption to synchronize clocks. The remarkable thing is that when they do this, all of physics works out consistently. Every experiment, every observation, every measurement confirms that this assumption leads to correct predictions. But here's the philosophical kicker. You could, in principle, assume that light travels at different speeds in different directions. And as long as you also adjusted your clock synchronization accordingly, you'd get the same experimental results. This is called the conventionality of simultaneity, and it's been a source of debate among physicists and philosophers for decades. However, the symmetric version where light speed is the same in all directions is by far the simplest. It requires no preferred direction in space, no special reference frame, no arbitrary choices. It's the most elegant solution, and elegance in physics usually points toward truth. More importantly, If light speed were different in different directions, you'd expect to see differences in physical laws in different directions. Stars in one part of the sky would behave differently from stars in another part. The cosmic microwave background would have weird anisotropies beyond what we observe. Particle physics would depend on which way your accelerator points. None of this is observed. The universe appears to be isotropic the same in all directions. And this isotropy is intimately connected to the constancy of the speed of light. Now, here's where this connects to our question about reaching light speed. The fact that all observers measure the same speed of light, regardless of their motion and regardless of direction, means that the speed of light is woven into the very fabric of space-time in a way that's independent of matter, energy, or motion. It's not like a speed limit on a highway that you could hypothetically break with enough power. It's more like the ratio between the circumference and diameter of a circle. It's pi, always, everywhere, regardless of the circle's size. The value of pi isn't enforced by some cosmic police force. It's a mathematical necessity that follows from the definition of a circle. Similarly, the speed of light is a geometric property of spacetime itself. It's the conversion factor between space and time, the ratio that tells you how much space equals how much time. In natural units that physicists often use, c equals 1, meaning space and time are measured in the same units. And the speed of light is just the number that converts between our arbitrary human units. Asking, why can't we exceed the speed of light, is like asking, why can't we make a circle where the circumference is 4 times the diameter instead of pi times the diameter? The question contains a misunderstanding. You're not asking about a physical limitation. You're asking why mathematics is the way it is. The physicist Max Tegmark has argued that the universe is mathematics, that physical reality is a mathematical structure, and what we call physical laws are just properties of that structure. Whether or not you accept this radical view, it's clear that the speed of light is mathematical in a deep sense. It's not an empirical fact that could have been different. It's a logical necessity given the structure of spacetime. This is why all the science fiction ideas about warp drives or hyperspace require fundamentally changing the structure of spacetime itself. You can't just push through the light barrier with enough force because there's no barrier to push through. There's just the geometry of spacetime, and that geometry doesn't allow paths that reach or exceed c for massive objects. Some theoretical physicists, like Miguel Alcubierre, have shown that Einstein's equations of general relativity might permit solutions where spacetime itself is warped in such a way that an object could be carried faster than light without locally exceeding c. The famous Alcubierre drive concept involves compressing spacetime in front of a spacecraft and expanding it behind, surfing on a wave of distorted spacetime. But here's the catch. Such solutions require exotic matter with negative energy density, something that violates all known physics. It's mathematically possible in the equations, but physically impossible with any known form of matter or energy. It's like saying, if I had a magic carpet, I could fly. True, but you don't have a magic carpet, and there's no known way to make one. Moreover, even if you could somehow create such exotic matter, recent analyses suggest that these warp drive solutions would be unstable, would require more energy than exists in the visible universe, and would likely violate causality in catastrophic ways, creating time travel paradoxes. The universe, it seems, has multiple layers of protection against FTL travel. Even if you try to cheat by warping spacetime instead of moving through it, you run into impossible energy requirements and causality violations. Here's the bottom line. The speed of light is isotropic, constant, and fundamental because it's not really a property of light. It's a property of spacetime itself. It's the exchange rate between space and time, the speed of causality, the cosmic speed limit, not because something enforces it from outside, but because it's built into the very structure of reality. And this brings us to perhaps the most fundamental reason of all why we can never reach the speed of light. because of what light actually is, and what it means to be a massive particle versus a massless one. Let's talk about what makes you different from a photon. I don't mean philosophically or spiritually. I mean physically, at the most fundamental level. The answer comes down to a single word: mass. You have mass. A photon doesn't. And this difference isn't just quantitative. It's not that you have a lot of mass and a photon has a little. A photon has exactly zero mass. Not approximately zero. Not vanishingly small. Exactly, precisely, mathematically zero. And this makes all the difference. Think back to that gamma factor. Gamma equals 1 square root 1v squared per c squared. For anything with mass, when v equals c, you're dividing by zero, and the result is infinite. Time dilation becomes infinite. Length contraction becomes infinite. Energy becomes infinite. Everything breaks. But for a massless particle, something interesting happens. The equations work out differently. The energy of a photon is E equals hf, where h is Planck's constant and f is frequency. The momentum is P equals EC equals hfc. Notice, neither of these equations involves mass at all. A photon doesn't have rest mass, so there's no rest frame for a photon. You can't slow a photon down. It's always moving at speed c, from the moment it's created until the moment it's absorbed. It doesn't accelerate from rest to light speed. It simply exists at light speed. That's the only speed it can have. From the photon's perspective, although it's misleading to talk about a photon having a perspective, time doesn't pass. The photon's clock is frozen at zero. A photon emitted from a star a billion light years away experiences zero time between emission and hitting your eye. From the photon's point of view, the entire journey is instantaneous, and the space it travels is contracted to zero length. This is what it means to be a massless particle. You exist on the boundary of space-time, on the light cone, where past and future meet in an eternal present. You don't experience time because you're moving along a null world line, a path through space-time with a space-time interval equals zero. Now contrast this with massive particles. An electron, for example, has a mass of about 9.109 times 10 kilograms. Tiny, but not zero. This tiny mass makes an infinite difference. An electron can be at rest. It can move slowly or quickly. It experiences time. It has a reference frame. And it can never, ever reach the speed of light. The question, why can't a massive particle reach the speed of light, is like asking, why can't a circle be a square? They're different categories of things. Massive particles and massless particles aren't just different amounts of the same thing, they're fundamentally different types of entities. Massive particles move through space-time on time-like paths that stay inside the light cone, where time flows and causality operates normally. Massless particles move on null paths, the surface of the light cone itself, where they're always moving at c and experiencing zero proper time. There's no continuous path from one to the other. You can't smoothly transition from being inside the light cone to being on the light cone by adding more energy. The faster you go, the more energy it takes to go even faster, and the energy requirement approaches infinity as you approach c. You'd need infinite energy to reach the boundary, and infinite energy doesn't exist. But here's where it gets even more interesting. Why do some particles have mass and others don't? This question stumped physicists for decades. The Standard Model of particle physics, developed in the 1960s and 70s, predicted that many fundamental particles should be massless. But experimentally, we know that electrons, quarks, and many other particles have mass. The solution came from a mechanism proposed by several physicists in the 1960s, but most famously by Peter Higgs. The Higgs mechanism suggests that all of space is filled with a field, the Higgs field, and particles acquire mass by interacting with this field. Think of it like moving through water. If you're a small, streamlined fish, you can move through water easily. If you're a large, irregular object, the water resists your motion more. The resistance you feel is analogous to mass. It's the Higgs field's resistance to your acceleration. Photons don't interact with the Higgs field at all, so they have zero mass and always travel at speed c. Electrons interact with the Higgs field a little, so they have a small mass. Quarks interact more strongly, so they have more mass. The W and Z bosons, particles that carry the weak nuclear force, interact very strongly with the Higgs field, giving them masses about 80 to 90 times that of a proton. In 2012, physicists at CERN announced the discovery of the Higgs boson, a particle that represents excitations of the Higgs field. This was a monumental achievement, confirming a prediction made decades earlier and completing the standard model of particle physics. Peter Higgs and Francois Englert were awarded the Nobel Prize in Physics in 2013. What the Higgs mechanism tells us is that mass isn't an intrinsic property that particles just have. It's the result of their interaction with a field that permeates all of space. Particles that don't interact with the Higgs field, like photons, are free to travel at the maximum possible speed, the speed of causality itself. Particles that do interact with the Higgs field are slowed down, held back, given inertia. Mass is the Higgs field's way of saying, you can't go that fast. And the amount of mass determines how hard it is to accelerate you, how much energy is required to bring you up to any given speed. But no amount of mass, no matter how tiny, allows you to reach c. Even a neutrino, which has a mass so small, we still haven't measured it precisely, probably less than a millionth the mass of an electron, cannot reach the speed of light. As long as your mass is greater than zero, even infinitesimally, you're categorically different from massless particles. You're stuck on time-light paths, forever inside the light cone. There's a conceptual leap here that's worth emphasizing. The speed of light isn't the speed of light. It's the speed of massless particles, the speed of causality, the maximum rate at which information can propagate. Light just happens to travel at this speed because photons are massless. If photons had mass, even a tiny amount, they would travel slower than c. In fact, physicists have searched for evidence that photons might have a tiny mass, because if they did, it would revolutionize physics. They've put extremely tight limits on the possible mass of a photon less than 10 electron volts, which is absurdly tiny, but so far, all evidence suggests it's exactly zero. The distinction between massive and massless particles is absolute. It's binary, not continuous. You either have mass or you don't. And if you have mass, you can't reach c, period. No technology, no matter how advanced, can change this, because it's not about technology. It's about the fundamental structure of reality. This mass gap is our fifth major barrier. But there's yet another aspect we haven't fully explored. What happens to the very structure of space and time as you approach light speed? How does acceleration itself work in a relativistic context? Let's dive into that next. All right, I want you to imagine you're in a spacecraft with a powerful rocket engine. From Earth's perspective, we've established that as you get faster, you get harder to accelerate. Your relativistic momentum grows without bound, and you asymptotically approach c without ever reaching it. But what about from your perspective inside the spacecraft? This is where things get beautifully weird. From your perspective, everything seems normal. You're sitting in your captain's chair, you fire the engines, and you feel pushed back into your seat with, let's say, 1 g of acceleration, the same as Earth's gravity. Nice and comfortable. You keep the engines running. From your perspective, you're accelerating at a constant rate. After 1 year of ship time, accelerating at 1 gram, you'd expect to be going pretty fast, right? Let's do the math. 1 g is about 9.8 meters per second squared. In 1 year, about 31.5 million seconds, that's a velocity change of about 309 million meters per second. Wait, that's faster than the speed of light. The speed of light is only 300 million meters per second. So after 1 year of constant 1g acceleration, you should be going faster than light. We've broken the speed barrier. We did it, except we haven't, because from Earth's perspective, your velocity never reaches c, no matter how long you accelerate. So what gives? Is relativity lying to you? No. What's happening is that your perception of time and distance is shifting continuously as you accelerate. From Earth's perspective, your clock is running slow and getting slower. From your perspective, the distance to your destination is contracting and continues to contract. These effects conspire so that you always measure yourself accelerating at 1 gram, but you never measure your velocity relative to Earth reaching c. This leads to a bizarre situation. You can keep accelerating forever from your perspective, always feeling 1g pushing you back in your seat, never maxing out. From Earth's perspective, your velocity approaches c asymptotically, getting closer and closer, but never reaching it. From your perspective, the entire universe ahead of you keeps contracting, and you keep getting closer to your destination at an ever-accelerating rate. After 1 year of ship time accelerating at 1 gram, you'd be moving at about 77% of light speed from Earth's perspective, and you'd have traveled about 0.56 light years from Earth's perspective. After 2 years of ship time, you'd be at 97% of light speed, having traveled about 2.9 light years from Earth. After 5 years of ship time, you'd be at 99.9% of light speed, having traveled about 83 light years. After 10 years, you'd be at 99.995% of light speed, having traveled about 950 light years. The center of our galaxy is about 26,000 light years away. You could reach it in about 12 years of ship time, even though 26,000 years would pass on Earth. Wait, that sounds like you're going faster than light. You're covering 26,000 light years in 12 years. But you're not, because of length contraction. From your perspective, the galaxy isn't 26,000 light years away. When you're moving that fast, it's contracted to about 12 light years away. You're still traveling at less than the speed of light through the contracted space. This is what's called proper acceleration, the acceleration you actually feel, measured in your own reference frame. You can maintain proper acceleration indefinitely. But coordinate acceleration, your acceleration, as measured by someone else, decreases as you approach c, approaching 0 as your velocity approaches c. From your perspective, you could accelerate at 1 gram for decades, centuries even if you somehow had enough fuel, and you'd subjectively experience normal, constant acceleration. You could cross the entire observable universe in a human lifetime, but you'd still never reach c, because from your perspective, the universe keeps contracting in your direction of motion, making the distances shorter and shorter. Meanwhile, from Earth's perspective, billions of years would pass. You'd be moving at 99.999999% of light speed, with as many nines as you want, but still not quite c, and the energy required to maintain your acceleration from Earth's perspective would be approaching infinity. This is sometimes called the twin paradox, though it's not really a paradox once you understand relativity properly. If you have a twin who stays on Earth while you zoom off at near light speed, when you return, you'll have aged less than your twin. This isn't symmetric. The traveling twin experiences acceleration and deceleration, which breaks the symmetry between the reference frames. This has been confirmed experimentally many times. Atomic clocks flown on airplanes tick slower than clocks left on the ground. Unstable particles created in cosmic ray collisions high in the atmosphere travel much farther than they should before decaying, because from our perspective, their internal clocks are running slow due to time dilation. GPS satellites require continuous corrections for both special and general relativistic time dilation effects. Every piece of evidence confirms that time really is relative, that it really does flow at different rates for observers in relative motion, and that the speed of light really is an absolute limit that can be approached but never reached. Now, here's a subtle but important point. When we say you can never reach the speed of light, we mean relative to any other massive object or any inertial reference frame. But here's a weird question. Relative to a photon, how fast are you moving? The answer is, the question doesn't make sense. A photon doesn't have a reference frame. There's no such thing as the photon's perspective in any rigorous sense. The Lorentz transformations that relate different reference frames break down. At v equals c, you can't transform into the reference frame of a photon because it doesn't exist. This is another way of seeing that the speed of light is special. It's the boundary between reference frames that can exist and reference frames that cannot. Massive particles live in reference frames. Massless particles don't. They exist on the boundary, the light cone, the edge between time-like and space-like regions of space-time. Your rocket ship, no matter how powerful its engines, can never cross that boundary. You can approach it as closely as you want, given enough energy and time, but you can never reach it. The boundary is infinitely far away in terms of the energy required to reach it. And here's something that will really twist your brain. Even if you somehow did reach the speed of light, from your perspective, you wouldn't notice anything special. Your clocks would be frozen, but you wouldn't experience frozen time, you wouldn't experience anything at all. The journey would be instantaneous and distanceless. You'd be everywhere on your path simultaneously, experiencing all moments as one. This is the paradox at the heart of reaching light speed. If you could do it, it would mean nothing, because you'd cease to have a meaningful existence in space-time. You'd exist outside of time, and existence outside of time is essentially non-existence from any meaningful perspective. So our sixth barrier is the nature of acceleration itself. You can accelerate continuously from your own perspective, but from any external perspective, your velocity asymptotically approaches c without ever reaching it. The universe has arranged things so that these two perspectives remain consistent, even though they seem contradictory. But we're still not done. There's one more fundamental aspect we need to explore. What happens in extreme gravitational fields? And how does general relativity, Einstein's theory of gravity, affect our understanding of the speed of light limit? So far, we've been talking about special relativity, Einstein's 1905 theory that deals with observers moving at constant velocities. But Einstein wasn't satisfied. Special relativity couldn't handle acceleration or gravity. So he spent the next decade developing general relativity, published in 1915, which revolutionized our understanding of gravity itself. In Newton's view, gravity is a force and invisible pull between massive objects. Earth pulls on you, you pull on Earth, the sun pulls on Earth, and so on. Simple, intuitive, and mostly correct for everyday situations. But Einstein had a radically different insight. Gravity isn't a force at all. It's the curvature of space-time itself. Massive objects bend the fabric of space-time, and other objects moving through that curved space-time follow curved paths. What we perceive as gravitational attraction is actually objects following straight paths through curved space. Think of it like this. Imagine a stretched rubber sheet. If you place a heavy bowling ball on it, the sheet curves around the ball. Now roll a marble across the sheet. The marble's path will curve toward the bowling ball, not because the ball is pulling on it, but because the sheet itself is curved. The marble is following the straightest possible path through curved space, what's called a geodesic. This is what Earth does to space-time. The sun does it even more dramatically. Black holes do it so extremely that space-time curves back on itself. Now, here's how this relates to the speed of light. In general relativity, the speed of light is still a constant locally in any small patch of space-time. Light always moves at c. But in curved space-time, the global structure gets complicated. Light still follows null geodesics paths to space-time, where the space-time interval is 0, but these paths are curved by gravity. This has been confirmed observationally. In 1919, Arthur Eddington led expeditions to observe a solar eclipse and measured the positions of stars near the sun's edge. The starlight was bent by the sun's gravity, exactly as Einstein predicted. This observation made Einstein world famous overnight. But here's something stranger. In extremely curved spacetime, like near a black hole, the structure of light cones themselves changes. Far from any masses, in flat spacetime, your future light cone opens up symmetrically in all directions. But near a massive object, the light cones tip over toward the mass. Near a black hole, this tipping becomes extreme. At the event horizon point of no return, the light cones tip over so far that all future directed paths, even those of light itself, point inward toward the singularity. Once you cross the event horizon, even traveling at the speed of light straight away from the center won't save you. Your future is guaranteed to end at the singularity. This is what makes a black hole black. Even light can't escape once it crosses the event horizon. Not because the gravity is pulling so hard that light can't overcome it, but because space-time itself is so warped that all future directed paths lead inward. Now you might think, but wait, if space-time is so warped that light can't escape, doesn't that mean something is moving faster than light? Doesn't the black hole pull light back faster than light can move away? No, this is a common misconception. Nothing is moving faster than light locally. At every point in space-time, light still moves at c relative to nearby observers. But the global structure of space-time is so warped that even moving at c locally isn't enough to escape. It's like being on a treadmill running faster than you can run. You're running at your maximum speed, but you're still moving backward from an external perspective. This reveals something profound. The speed of light limit is local, not global. Locally, in any small region of space-time, nothing can outrun light. But globally, the structure of space-time can be such that even light can't connect certain regions. In fact, there are regions of space-time that are causally disconnected from each other. No signal, not even light, can travel between them. The most dramatic example is the observable universe. Due to the expansion of space itself, which we'll get to in a moment, there are galaxies so far away that light from them will never reach us, and light from us will never reach them. Not because the light is too slow, but because the space between us is expanding faster than light can cross it. Wait, space can expand faster than light? Doesn't that violate relativity? No, because space itself isn't moving through space-time. It is space-time. The speed of light limit applies to objects moving through space, not to the expansion of space itself. Think of it like dots on a balloon. As you inflate the balloon, the dots move apart from each other, but no individual dot is moving through the balloon's surface faster than any local speed limit. The surface itself is expanding. This is described by general relativity's cosmological solutions, particularly the Friedmann equations derived from Einstein's field equations. Edwin Hubble discovered in 1929 that distant galaxies are receding from us, and the farther away they are, the faster they are receding. This isn't because they're moving through space away from us. It's because the space between us and them is expanding. Current observations show that the expansion is accelerating, driven by something we call dark energy, though we don't really know what it is. Galaxies more than about 14 billion light-years away are receding from us faster than the speed of light, not because they're moving through space that fast, but because the space itself is expanding that rapidly. This means we're causally disconnected from huge portions of the universe. There are galaxies we can see now, because their light was emitted when they were closer, and the expansion was slower, but we'll never be able to visit them, communicate with them, or even receive new light from them, because the space between us is expanding faster than light can cross it. So even if you had a spacecraft that could travel arbitrarily close to the speed of light 99.9999999% of c, there would still be destinations in the universe you could never reach, because the space between you and them is expanding faster than you can cross it. This gives us a seventh barrier. Even if we could somehow overcome all the other obstacles and travel arbitrarily close to the speed of light, the expansion of the universe itself creates unreachable regions. The cosmic speed limit, combined with cosmic expansion, puts hard limits on what portions of the universe we can ever access. But general relativity introduces another fascinating aspect: gravitational time dilation. We've talked about how motion slows time, but gravity does too. The stronger the gravity, the slower time flows. This isn't just an effect of motion. It's an effect of the curvature of space-time itself. Near a massive object, time passes more slowly than it does far away. On Earth's surface, time passes slightly slower than it does for GPS satellites in orbit. The difference is tiny, about 45 microseconds per day, but it's measurable and must be corrected for GPS to work. Near a black hole, the effect becomes extreme. If you were hovering just outside the event horizon of a supermassive black hole, time for you would pass at a tiny fraction of the rate it passes for someone far away. From your perspective, everything seems normal. But if you looked up at the distant universe, you'd see events happening in fast forward. Stars would evolve and die in what seems like moments. Meanwhile, someone watching you from far away would see you moving in extreme slow motion. As you approach the event horizon, you'd appear to slow down more and more, asymptotically approaching the horizon, but never quite reaching it from their perspective. Your image would freeze, becoming redder and dimmer as your light becomes increasingly redshifted and time-dilated. This is eerily similar to what happens as you approach the speed of light. In both cases, approaching c through motion or approaching an event horizon through gravity-time dilation approaches infinity. You experience time normally, but external observers see your clock slow to a stop. This isn't a coincidence. In general relativity, motion and gravity are intimately related. Einstein's equivalence principle states that being in a gravitational field is locally indistinguishable from being in an accelerating reference frame. If you're in a windowless room, there's no experiment you can do to tell whether you're sitting on Earth's surface in a gravitational field or in a rocket in deep space, accelerating at 1 gram. This deep connection between motion, acceleration, and gravity all reinforces the fundamental nature of the speed of light limit. It's not just a limit on motion. It's woven into the causal structure of space-time itself, into how gravity works, into how acceleration works, into everything. Now, I mentioned black holes have singularities, points of infinite density, where space-time curvature becomes infinite. At a singularity, general relativity itself breaks down. The equations produce infinities, which usually means the theory has reached its limits and a more fundamental theory is needed. Most physicists believe that quantum mechanics and general relativity must be unified into a theory of quantum gravity to describe what actually happens at singularities. We don't have such a theory, yet it's one of the biggest unsolved problems in physics. String theory, loop quantum gravity, and other approaches are being explored, but we don't have experimental evidence to guide us. But here's what's interesting. Even in these speculative theories of quantum gravity, the speed of light remains a fundamental limit. Some theories propose that space-time itself might be quantized, made up of discrete chunks at the Planck scale, about 10 meters. But even if space-time is fundamentally grainy rather than smooth, the effective speed of light remains the cosmic speed limit. So our understanding from general relativity reinforces everything we learned from special relativity. The speed of light isn't just a speed limit on motion through space. It's a fundamental property of space-time itself, of causality, of how cause and effect propagate through the universe. Gravity curves space-time, but it doesn't change this fundamental limit. And this brings us to perhaps the most practical barrier: Even if somehow, impossibly, you could reach the speed of light, what would happen to you and your spacecraft? The answer involves one of the most destructive forces in the universe. Let's say you're stubborn. You've heard all the theoretical reasons why you can't reach the speed of light, but you're going to try anyway. You've somehow built a spacecraft that's approaching relativistic speeds, let's say 99% of the speed of light. Congratulations. You're about to die in one of the most spectacular ways imaginable. Here's why. Space isn't empty. Even the best vacuum in interstellar space contains about 1 atom per cubic centimeter. That doesn't sound like much. It's far emptier than the best vacuum we can create on Earth. But when you're moving at relativistic speeds, even individual atoms become deadly. Remember kinetic energy. K equals gamma to 1 mg squared. At 99% of light speed, gamma is about 7. So a single hydrogen atom, mass about 1.67 times 10 kilograms, has a kinetic energy of about 610 times 7, 310 squared joules, which works out to about 110 joules from your reference frame. That's about as much energy as 100 million electron volts, comparable to a high-energy gamma ray. A single hydrogen atom hitting your spacecraft at 99% of light speed would have the energy of a high-energy cosmic ray. Now, you're not hitting one atom. At 99% of light speed, traveling through space with a density of 1 atom per cubic centimeter, you're encountering about 310 atoms per second per square meter of your spacecraft's cross-section. That's 30 billion atoms per second, each one hitting you with the energy of a gamma ray. The front of your spacecraft would be bombarded by what's effectively a continuous beam of intense radiation. This isn't just a little radiation. We're talking about a particle beam with enough energy to vaporize matter. Your spacecraft's hull would heat up, ablate, and disintegrate. And it gets worse as you go faster. At 99.9% of light speed, each atom has about 22 times more energy. At 99.99%, about 70 times more. The radiation bombardment increases quadratically with your gamma factor. But wait, there's more. Those hydrogen atoms aren't the only problem. The cosmic microwave background, the afterglow of the Big Bang, which fills all of space, consists of photons with a typical energy of about 0.00024 electron volts, completely harmless at everyday speeds. But due to relativistic Doppler shift, when you're moving at 99% of light speed toward these photons, they blue shift dramatically. From your reference frame, they're no longer low-energy microwave photons. They're high-energy gamma rays and even higher-energy particles. The entire universe ahead of you becomes a blazing wall of deadly radiation. This was calculated in detail by physicist William Edelstein and colleagues in a paper published in 2012. They showed that at speeds above about 99.9999% of light speed, the blue-shifted cosmic microwave background becomes so energetic that it would deliver a lethal radiation dose to any biological crew in less than a second, even through meters of shielding. The faster you go, the worse it gets. At 99.999999% of light speed, 9 nines, the CMB photons would be blue-shifted to energies comparable to particles in the Large Hadron Collider. Your spacecraft would be flying through the equivalent of a particle accelerator beam. And we haven't even talked about actual dust particles. A single dust grain, let's say 0.1 micrometers in diameter, mass about 10 kilograms, hitting your spacecraft at 99% of light speed would have a kinetic energy of about 630 kilojoules, equivalent to about 150 grams of TNT. One tiny speck of dust would hit like a small bomb. Even at merely 10% of light speed, already far beyond anything we can currently achieve, a dust grain impact would release energy comparable to a hand grenade. At 50% of light speed, that same dust grain would hit with the force of about 50 kilograms of TNT. At 90%, about 800 kilograms of TNT. At 99%, about 150 kilograms. There's simply no material we know of that could withstand this bombardment. Even if you could somehow generate the energy to accelerate to near light speeds, which you can't, your spacecraft would be sandblasted into plasma before you got very far. Some science fiction authors have proposed using magnetic or electric fields to deflect charged particles. But most interstellar atoms are neutral, and those fields wouldn't help. And you can't deflect photons with electromagnetic fields at all. You could try putting a massive shield in front of your spacecraft, maybe a block of ice or metal several meters thick. But at relativistic speeds, any collision with that shield would produce a shower of secondary particles, pions, muons, gamma rays that would still irradiate the spacecraft behind it. Plus, you'd have to accelerate that massive shield along with your ship, requiring even more impossible amounts of energy. The relativistic rocket equation, derived by physicist Tsiolkovsky and extended to relativistic speeds, shows that the amount of fuel you need increases exponentially with your desired final velocity. To accelerate a spacecraft to even 10% of light speed using chemical rockets would require a fuel-to-payload mass ratio of about 10 more fuel mass than exists in the entire observable universe. Even with perfect matter-antimatter annihilation, the most efficient energy conversion theoretically possible getting to 70% of light speed would require carrying about 100 times your spacecraft's mass in antimatter fuel. And we currently produce antimatter at a rate of about 10 nanograms per year at astronomical cost. The entire world's supply of antimatter wouldn't be enough to power a light bulb for more than a few minutes. But let's say you solve all these problems. Let's say you have unlimited energy, perfect shielding, and you're somehow approaching the speed of light. Here's one final, unavoidable problem. Where are you going? At relativistic speeds, navigation becomes nearly impossible. Light from stars ahead of you is blue-shifted, making them look different. Light from stars behind you is red-shifted. Due to relativistic aberration, stars appear to bunch up ahead of you while the sky behind you goes dark. The normal star patterns you'd use for navigation are completely distorted. Worse, at extreme relativistic speeds, time dilation means that the universe is evolving rapidly from your perspective. Stars are being born and dying in what seems like fast forward. If your journey takes 10 years of ship time at 99.999% of light speed, over 20,000 years pass on Earth. The constellations change. The civilizations you left behind might have risen and fallen. And perhaps most disturbingly, you can't stop quickly. At relativistic speeds, you have enormous kinetic energy. To decelerate, you need to get rid of that energy somehow. You can't just fire reverse thrusters. You'd need just as much energy to slow down as you used to speed up. If you tried to aerobrake by skimming through a planet's atmosphere, you'd hit the atmosphere with so much energy that you'd trigger a nuclear explosion-level event, likely destroying yourself and possibly causing massive damage to the planet. This is our eighth barrier, practical impossibility. Even if all the theoretical barriers somehow didn't exist, the engineering challenges of relativistic travel are insurmountable. The universe is hostile to fast-moving objects, and that hostility increases exponentially with speed. So we have theoretical impossibilities, infinite energy requirements, dividing by zero in the equations, causality violations. We have practical impossibilities, radiation bombardment, impossible fuel requirements, navigation challenges. And we have one more fundamental barrier we haven't fully explored, the quantum mechanical nature of reality itself. Up until now, we've been discussing relativity, Einstein's revolutionary insight that space and time are relative and interconnected. But there's another revolution in 20th century physics that's equally profound, quantum mechanics, which describes the bizarre behavior of matter and energy at the smallest scales. Here's the amazing thing. Relativity and quantum mechanics don't naturally fit together. They're both correct within their domains: relativity for large-scale spacetime and gravity, quantum mechanics for small-scale particles and forces, but they're fundamentally incompatible in their mathematical structures. Einstein's general relativity describes spacetime as smooth and continuous, a fabric that can be curved and warped. Quantum mechanics describes reality as fundamentally probabilistic and discrete, made of quantized chunks. When you try to apply both theories to the same situation, like what happens at the center of a black hole or at the moment of the Big Bang, you get infinities and nonsense. Physicists have been trying to reconcile these theories for nearly a century. We need a theory of quantum gravity, but we don't have one yet. What we do have are some insights into where the boundaries might be, the scales at which quantum effects and gravitational effects become equally important. This is called the Planck scale, named after Max Planck, one of the founders of quantum mechanics. At the Planck scale, spacetime itself might not be smooth and continuous. It might be foamy, quantized, fundamentally discrete. The Planck length is about 1.6 times 10 meters, unimaginably tiny. An atom is to the Planck length as the observable universe is to a tree. The Planck time is about 5.4 times 10 seconds, the time it takes light to cross one Planck length. The Planck energy is about 1.22 times 10 GeV, about the energy of a mosquito concentrated into a single particle. Why do these scales matter for our question about reaching light speed? Because they might represent fundamental limits on how finely we can divide space, time, and energy. If spacetime is quantized at the Planck scale, then motion itself might be fundamentally discrete rather than continuous. Some theories of quantum gravity suggest that there might be a maximum velocity that's slightly less than c, or that the speed of light itself might have tiny variations at extremely high energies. These are called Lorentz violation theories, and physicists have looked very carefully for any evidence of them. So far, we've found nothing. The speed of light appears to be exactly constant at all energies we can test, up to the highest energy cosmic rays ever detected, particles with energies more than 100 million times higher than anything we can produce in the LHC. These particles have been traveling through space for billions of years, and they still respect the cosmic speed limit perfectly. If there were any quantum corrections to special relativity that allowed faster than light travel, we should see effects in these ultra-high energy cosmic rays. The fact that we don't suggests that the speed of light limit is even more fundamental than we might have thought. It survives, even when quantum effects become important. But here's where things get really strange. Quantum mechanics introduces a fundamental uncertainty principle, discovered by Werner Heisenberg in 1927. You cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of our measuring instruments. It's a fundamental property of reality. Particles don't have exact positions and momenta simultaneously. They exist in superpositions of multiple possible states until measured. Now, here's a weird question. What happens to the Heisenberg uncertainty principle at relativistic speeds? The uncertainty principle is delta x times delta p is greater than or equal to A2, where A is the reduced Planck constant. But momentum in relativity is pgmv, which means uncertainty in momentum relates to uncertainty in velocity in a complicated way when gamma is large. As you approach the speed of light, gamma approaches infinity, which means a small uncertainty in velocity corresponds to a huge uncertainty in momentum. This suggests that at extreme relativistic speeds, quantum effects become increasingly important, and the particle's behavior becomes increasingly probabilistic. In fact, when we try to apply quantum mechanics to particles moving at relativistic speeds, we get quantum field theory, the framework that describes the standard model of particle physics. In quantum field theory, Particles can be created and destroyed, and the vacuum itself is filled with virtual particles, constantly popping in and out of existence. The Unruh effect, predicted by physicist William Unruh in 1976, suggests that an observer accelerating through empty space would perceive that space as filled with thermal radiation, a bath of particles that appear due to the acceleration itself. The temperature of this radiation is proportional to the acceleration. For typical accelerations, this Unruh temperature is tiny, undetectable. But as you accelerate harder and harder trying to reach light speed, the Unruh temperature increases. At extreme accelerations, the quantum vacuum around you would appear to be an inferno of particle creation and annihilation. This gives us hints that quantum mechanics might provide yet another barrier to reaching light speed, not just the classical barriers of infinite energy and zero time, but quantum mechanical barriers involving the structure of the vacuum itself. There's also the question of quantum tunneling. In quantum mechanics, particles can tunnel through energy barriers that they classically couldn't cross. Could a particle quantum tunnel through the light speed barrier? The answer appears to be no. The math of quantum mechanics is built on the same space-time structure as relativity, the Schrödinger equation for non-relativistic quantum mechanics, and the Dirac equation for relativistic quantum mechanics both respect the speed of light limit. Quantum tunneling allows particles to appear on the other side of potential energy barriers, but it doesn't allow them to exceed the speed of light while doing so. In fact, when physicists carefully analyze quantum tunneling, they find that even though it looks like a particle teleports through a barrier instantaneously, no information is transmitted faster than light. The speed at which information can propagate, the speed of causality, remains c. Some interpretations of quantum mechanics, like the many worlds interpretation proposed by Hugh Everett in 1957, suggest that all possible outcomes of quantum measurements actually occur, but in different branches of reality. If this is true, could there be branches where particles exceed the speed of light? No, because the same laws of physics, including relativity, apply in all branches. The speed of light limit isn't something that varies from branch to branch. It's built into the structure of space-time itself, which is the same across all branches. Quantum entanglement, the phenomenon where measuring one particle instantly affects another particle, no matter how far away, might seem like it violates the speed of light limit. Einstein famously called it spooky action at a distance, and thought it proved quantum mechanics was incomplete. But we now know quantum mechanics was right, and Einstein's objections were wrong. Experiments by physicists like Alan Aspect in the 1980s and many others since have confirmed that entanglement is real. However, and this is crucial, entanglement doesn't allow faster-than-light communication. The correlations between entangled particles are instantaneous, but you can't use them to send information faster than light. The no-signaling theorem proves this rigorously. Think of it this way. Imagine you and a friend each have a coin that's entangled in a weird quantum way. When you flip your coin and it comes up heads, your friend's coin will definitely come up tails when they flip it, no matter how far apart you are. But here's the thing. You can't control whether your coin comes up heads or tails. It's random from your perspective. So you can't use this to send a message. You can't make your friend's coin come up tails by forcing yours to come up heads, because you can't force yours to come up heads in the first place. Entanglement creates correlations, but not causal influences that propagate faster than light. The speed of light limit on information transmission, on causality, remains intact. So quantum mechanics, far from providing a loophole around the speed of light limit, actually reinforces it. Every quantum theory that's been developed respects relativistic causality. Every experiment confirms that information cannot travel faster than light, even through quantum channels. This is our ninth barrier, quantum mechanical consistency. The marriage of quantum mechanics and relativity, quantum field theory, depends crucially on the speed of light limit. If that limit could be broken, the entire theoretical framework that describes particle physics would collapse. Okay, so we can't accelerate to the speed of light through normal means. Every law of physics conspires against us. But what about the clever workarounds that show up in science fiction? What about warp drives, wormholes, and other exotic solutions? Could any of these actually work? Let's start with the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. The idea is brilliant. Instead of moving through space, you warp space itself. You compress space-time in front of your spacecraft and expand it behind you, creating a warp bubble that carries you along. Locally, within the bubble, you're not moving at all, but the bubble itself can move faster than light, carrying you with it. The math actually works within general relativity. Einstein's equations allow solutions where space-time is distorted in this way. So problem solved, right? We just need to build a warp drive. Not so fast. Here's the problem. To create the Alcubierre metric, you need something called exotic matter with negative mass or negative energy density. And we're not talking about a little bit. To create a warp bubble big enough for a spacecraft, you'd need negative energy equivalent to the mass energy of Jupiter, concentrated into a thin shell around your ship. Does exotic matter exist? Maybe, in very specific quantum situations. The Casimir effect, discovered experimentally by Dutch physicist Hendrik Casimir in 1948, shows that two parallel metal plates in a vacuum will attract each other due to quantum vacuum fluctuations. The space between the plates has less energy than empty space outside them, a form of negative energy. But the Casimir effect produces incredibly tiny amounts of negative energy, nowhere near enough to warp spacetime on macroscopic scales. And we have no idea how to amplify it or control it to create something like an Alcubierre bubble. Moreover, later analyses by physicists like Francisco Alcubierre himself and Chris van den Broek showed that the Alcubierre drive has serious problems. First, you can't steer it from inside the bubble. The causal structure is such that no signal from inside the bubble can reach the front edge where you'd need to modify the field to change direction. You'd have to set your course before activating the drive and hope nothing gets in your way. Second, as you travel, you'd accumulate a shell of high-energy particles at the front of the bubble, basically building up a doomsday weapon that would be released in a devastating burst when you arrive at your destination and deactivate the drive. You'd destroy everything in front of you. Third, and most fundamentally, physicist Sergei Krasnikov showed that the Alcubierre metric requires closed, time-like curves paths through spacetime that loop back on themselves, allowing time travel into the past. This means the warp drive would create causality violations, allowing all the paradoxes we discussed earlier. The universe seems to protect itself against warp drives through a combination of impossible energy requirements, causality violations, and practical impossibilities. What about wormholes shortcuts through spacetime that connect distant regions? These also appear in Einstein's equations, first discovered by Ludwig Flamm in 1916 and popularized by Einstein and Nathan Rosen in 1935. Hence, Einstein-Rosen bridges. The problem: every traversable wormhole solution requires exotic matter to hold the throat open. Without it, the wormhole collapses faster than light can cross it. And we're talking about even more exotic matter than the Alcubierre drive needs, enough negative energy to fight against the entire gravitational collapse of spacetime. Physicist Kip Thorne and colleagues calculated in the 1980s that a human traversable wormhole might require negative energy equivalent to the mass of Jupiter distributed through the wormhole throat. Again, we have no idea how to create or manipulate such amounts of exotic matter. Moreover, even if you could somehow create a wormhole, physicist Stephen Hawking and others showed that quantum effects would likely destabilize it. When you try to use a wormhole, Vacuum fluctuations from quantum fields would feed back and amplify, creating infinite energy densities that would destroy the wormhole just as you try to traverse it. This is related to Hawking's chronology protection conjecture. The universe seems to forbid time machines and causality violations. What about quantum teleportation? This is a real phenomenon that's been demonstrated in laboratories. Quantum information can be transferred from one particle to another instantaneously through entanglement. Could we use this to transport humans faster than light? No, for several reasons. First, quantum teleportation requires sending classical information through normal channels at light speed or slower to complete the process. The person's quantum state would only be reconstructed after this classical information arrives, so you're still limited by the speed of light. Second, quantum teleportation destroys the original quantum state when creating the copy. If you teleported a person, you destroy the original person atom by atom while reading out their quantum state. This is fundamentally required by the no-cloning theorem of quantum mechanics. You can't create an exact copy of an unknown quantum state without destroying the original. Third, the amount of classical information needed to describe a human at the quantum level is staggeringly large, perhaps 10 bits or more. Transmitting this at light speed would take far longer than the age of the universe. What about Tolkien's hypothetical particles that always move faster than light? These were proposed by physicist Gerald Feinberg in 1967 as a mathematical curiosity. If they exist, they'd have imaginary mass, as in the square root of a negative number, and would move faster as they lose energy. But Tolkien's have never been detected, and their existence would create massive problems. They'd allow causality violations and time travel into the past. Moreover, if Tolkien's existed and could interact with normal matter, the vacuum would be unstable. Tolkien's would spontaneously be created everywhere, rapidly filling the universe with faster-than-light particles until some equilibrium was reached. The fact that we don't observe this suggests Tolkien's don't exist. Most modern physicists believe Tolkien's are mathematical artifacts of certain equations, not real particles. The consensus is that they're inconsistent with known physics and don't actually exist in nature. What about manipulating the fabric of space-time in other ways? What if we could create shortcuts through higher dimensions, like in some string theory scenarios? String theory, which proposes that fundamental particles are actually tiny vibrating strings, requires extra dimensions beyond the 3 of space and 1 of time we experience. Most versions of string theory require 10 or 11 total dimensions. The extra dimensions are presumably compactified, curled up so small we don't notice them. Could these extra dimensions provide shortcuts that effectively allow faster-than-light travel through our familiar 3 dimensions? It's an intriguing idea, but there's no evidence for it, and no clear mechanism for how we'd access these extra dimensions. Moreover, even in higher dimensional spaces, there are still local speed limits. String theory is built to be consistent with relativity. It respects local causality. If there were shortcuts through extra dimensions that violated causality in our observable universe, the entire theoretical framework would be inconsistent. The fundamental issue with all these proposals, warp drives, wormholes, higher dimensions, is that they require physics that we don't know exists, and that may be fundamentally impossible. They all involve exotic matter, negative energy, or other ingredients that seem to be forbidden by the known laws of physics. It's like saying, I can lift this mountain if I just had a crane big enough. True, but where are you getting the crane? Where are you getting the exotic matter? The known laws of physics don't provide it, and every attempt to create it runs into fundamental barriers. The universe has multiple layers of protection against faster-than-light travel. Even when you find an apparent loophole in one set of equations, other physical principles step in to close it. It's almost as if the universe is conspiring to protect causality and the logical consistency of space-time. This is our 10th barrier. Every clever workaround requires impossible physics. The universe doesn't just make it hard to exceed light speed, it makes it logically impossible through multiple redundant barriers. But there's one more aspect we haven't fully explored. What does all this mean for our place in the universe and our cosmic future? Let's think about the implications. Let's take a step back and think about what all of this means. We've established beyond any reasonable doubt that we can never reach the speed of light, and that even getting close requires impossible amounts of energy. What does this mean for humanity's future? For our dreams of exploring the cosmos? For our place in the universe? First, let's be clear about the scale of the challenge. The nearest star system, Alpha Centauri, is 4.37 light-years away. With our current fastest spacecraft, the Parker Solar Probe, which reached speeds of about 120 kilometers per second, it would take about 10,000 years to get there. That's longer than all of recorded human civilization. If we could somehow build a spacecraft that travels at 10% of light speed, which would require revolutionary breakthroughs in propulsion, the trip would take 43.7 years. At 50% of light speed, requiring even more impossible amounts of energy, the trip takes 8.7 years, still nearly a decade. There are maybe 30 to 50 stars within 15 light-years of Earth. Beyond that, the distances become truly staggering. The center of our galaxy is 26,000 light-years away. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. The edges of the observable universe are about 46 billion light-years away, larger than you'd expect due to the expansion of space. Even if we could travel at 99.999% of the speed of light, requiring impossible amounts of energy, impossible shielding, impossible engineering, crossing the observable universe would take 46 billion years from Earth's perspective. From the traveler's perspective, time dilation would make the journey seem much shorter, but everyone they knew on Earth would have been dead for billions of years. And remember, due to the accelerating expansion of space, driven by dark energy, most of the observable universe is already unreachable. Light from those distant galaxies is reaching us, but we can never reach them because the space between us is expanding faster than we can cross it, even at light speed. Cosmologist Lawrence Krauss has calculated that in about 100 billion years, the expansion of space will have carried all distant galaxies beyond our cosmic horizon. Future civilizations will observe a universe that appears to contain only their local group of galaxies, with no evidence of the billions of other galaxies that we can see today. The observable universe is shrinking for any stationary civilization. Think about what this means. The universe is putting more and more of itself beyond our reach every moment. Stars we can see today will eventually cross beyond our cosmic horizon and become forever inaccessible. The light speed limit, combined with cosmic expansion, creates a cosmic prison from which there is no escape. This might seem depressing, but there's another way to look at it. The speed of light limit shapes the structure of civilization itself. Without faster-than-light communication or travel, any interstellar civilization would be fundamentally fragmented. A colony on a planet 10 light-years away would have a 20-year delay for any round-trip communication with Earth. They'd be effectively independent, their own civilization with its own culture, economy, and politics. The science fiction dream of a unified galactic empire is impossible. There's no way to maintain political unity across light-year distances when every message takes years to arrive. Even a hypothetical galactic senate, where representatives from different star systems meet to make policy, would be impractical. News of events from distant systems would be years or centuries out of date by the time it arrived. Instead, any spacefaring civilization would be a network of independent colonies, occasionally exchanging messages and perhaps travelers on one-way journeys lasting decades or centuries, but fundamentally separate. Each star system would be its own bubble of causally connected civilization. Some futurists, like physicist Paul Davies, have argued that this isn't necessarily bad. The fragmentation of humanity across star systems could be a form of resilience. If one civilization collapses or one planet suffers a catastrophe, others would survive and continue. We'd be spreading our eggs across many baskets, ensuring the long-term survival of human or post-human intelligence. But it also means we'll always be fundamentally limited in our reach. The universe is vast, perhaps infinite, and we can only ever access a tiny portion of it. Our descendants might spread across thousands of star systems, but they'll never visit other galaxies. They'll never know firsthand what lies in the vast cosmic voids between galactic superclusters. They'll be forever confined to our little corner of space-time.